This video is a quick overview of the things you're going to need to know for the Unit 5 exam and those same items that would show up on the final exam. So there are two concepts in this unit. The first one we looked at in the first couple lessons is the rational functions. And we looked specifically at, in the first unit, the equation y equals k divided by x. In this case, there's one thing that k cannot be, and it cannot be 0. This is the simplest of the rational equations. From a quick graph in Desmos, the basic shape looks like this. And it has two asymptotes. There's a vertical asymptote at x equals 0, and a horizontal asymptote at y equals 0. Of course, this x equals 0 is a horizontal asymptote is because we cannot divide by 0. And then the domain of this function is all real numbers except for 0. Now there's a couple ways we can write this. In interval notation, of course we can write it out in words. In interval notation it would look like this to show the exclusion of that 0. If we were doing set builder notation, I don't know that we've done this yet in this class before, but just in case you ever encounter this in the future, those are three different ways to show the domain of that function. So that's essentially everything. And we can also state the range, since we know the horizontal asymptote, it's all real numbers except for y equals 0. And I won't repeat the above things because it's the same thing here. So then we looked at graphs of the form y equals k over x to the n. And these graphs have all the same characteristics as the previous one, with the one exception that the shape of this graph, when n is even, looks like this. Oh, you can't even see what I'm writing. There we go. So y equals k to the n. So this is for when n is even. Otherwise, it looks like the previous graph when n is odd. And it has the same domain, it has the same range, and it has the same asymptotes. All of that is unchanged. The one thing we added in here is the language of inverse variation. So we noted that inverse variation has the equations that are written in this form. Where is it? Well, we say this: y varies inversely as the nth power of x. Now, if the power on x is 1, so if n equals 1, we would just say y varies inversely as x. So we wouldn't include the nth power of x. And then we know that the equations in this form are y equals k divided by x to the n. We call this k the constant of variation, and it has to be positive. Okay, that's it for that section. And then moving on to, that was 5.3. On to 5.4, we looked at equations in the form of y equals k divided by some function g of x. Now, if g of x is equal to x, or x to the n power, we're back with all the previous functions. If not, so if we have, say, x minus 1 or x plus 2, to find the domain and the range and the asymptotes, we have to do a little bit of work. So the domain is always all real numbers except for when g of x equals 0. So the solution from this is x cannot equal whatever this value is that we solve. that makes this denominator equal to 0. So that's the value that we're dividing by. It is not allowed. The shapes of these functions are dependent upon whatever the g of x is. So you're going to want to work with Desmos to figure out what does the graph look like. The vertical asymptote is x equals the same value as this one. So it's solve g of x equals 0, and there you found the x, the vertical asymptote. And then the horizontal asymptote is the same as before. It's y equals 0 when things are in this form. So notice it's a constant divided by some sort of function. Okay, and then in 5.4 we looked at solving these rational equations, and we looked at the graphical method. That should be your go-to method. That's where you graph both sides of the equation and see where they intersect. However, we did look at an example of if we have two fractions each equal to each other, a over b equals c over d, then we did the cross multiplication to solve. So that got us a times d equals b times c. And say we're solving for a, we then divide both sides by d, and you would get your a equals b times c divided by d. Again, for me, I prefer the graphical approach over all this. This is called cross multiplication. And we looked at this in class a little bit. Then, when we have functions in the form of this, our textbook uses this notation. Q of x equals f of x over g of x. And we had some very specific things for f and g of x that we looked at. F of x and g of x were linear equations. So when that's true, the domain is the same as above. It's all reals. I'm going to use the notation for real numbers, except x cannot equal the solution to setting the denominator equal to 0. The vertical asymptote, same thing. X equals whatever this value is. Again, you're solving g of x equal to 0. And then the horizontal asymptote, turns out when these two things are linear, you're going to get a function that looks like this. I'm going to write it in equation notation. You might have ax plus b over cx plus d, or some version of that. So the horizontal asymptote ended up being always this a divided by c. So you just took the coefficients of the x values and divided them, and you ended up with the horizontal asymptote. There are, of course, far more complicated versions of these rational functions, but we're sticking for this course to these more basic look at things. Okay, then we had this big equation that we used, and it was, I'll just put in here, what do we want to call this? This was the, I don't know, it was the time equation. So we'll say total time equation. And that is, if you have different things, people or objects working at different times, it was t1 plus t2 plus 1 over t3 equals 1 over t for total time. And we could have multiple of these added together, or just basic ones of them added together. And we looked at adding these fractions. So we added these to solve by hand. That was number 1, and then number 2 we cross multiplied. We used the cross multiplication. So what it ended up, how we did it in class, is we had to multiply each fraction by what it was missing. So I'll rewrite it here and just do it symbolically. Since all of these are missing the other denominator, I would multiply this one by T2 over T2, that's equal to 1, and T3 over T3. This one is missing a T1 and a T3, so we'd multiply by T1 over times T3. And then this one is missing a T2 and a T1. Oops, I should have put those in order, whatever. So what we end up with is T2 times T3 plus T1 times T3 plus T1 times T2. There I put them back in order, all divided by T1 times T2 times T3. And then at this point, we could do our cross multiplication and do our thing. Now, the problems we actually worked with were not nearly as crazy looking as this. I realize that's pretty bizarre looking. We tended to look at just two fractions we were adding together. Following from that. So after that, we skipped 5, 6, and we jumped to 5, 7, and 5, 8. And there we looked at radical functions. And I started class with a quick reminder of some things. That was, recall that if we had x to the 1 over n, that was equal to the nth root of x. So the right side was radical, the left side was rational exponents. So not a rational function, but it has a rational exponent right up here. And then we looked at how if we had y equals the square root of some linear function, the graph looked something like this. So it was half of a parabola. And then if we had y equals the negative of some linear function, its basic shape looked like this. We then used, we looked at all kinds of different looks of those shapes. And we talked about the falling object stuff and how you solved by squaring both sides, and that was basically it. For your project, you of course noted that we used this, was it like this? Provided your table had x1s and y1s. Maybe these values were switched, maybe it was b plus a. It doesn't particularly matter, but that was the square root modeling function. So that was it for Unit 5.